So I'm going to start a new topic today, which is ordinary differential equation. I know that most of you, probably all of you, are familiar with this to some extent, and I'd like to go fast to cover the basics. And if you think I'm going too fast, stop me and ask me questions. I'll be happy to explain the details. Some of you mentioned that the first topic, vectors and matrices, were kind of slow to you, and you expected a fast pace for ODEs and PDEs. So I'm going to be a little fast today. And have you also seen numerical solution like Euler scheme and MATLAB solution of ODEs? Yes? No? Okay. So that I'm going to take some time to explain at a more detail then. Let me start with where we are kind of ending our Monte Carlo simulation discussion. Suppose you have this random walk and you are already thinking, oh, again, Monte Carlo, no more Monte Carlo. And suppose instead of -1, you specify distances L, 2L, 3L, minus L, minus 2L, minus 3L. So each spacing is of length L, and suppose the time you take for one jump is t. Okay? And you start with a random walk, which all of you now know. If you go back and forth with equal probability half, the average is 0, x squared average increases linearly with time. Now my question is, can you think, okay, first let me ask you this. What happens if the random walk becomes asymmetric? I'm not talking about waiting time. So for example, I have probability 2/3 going into the right and probability 1/3 going into left. Do you have any idea how these things change? Like if there is a, yeah, sure.
Well, they're no longer centered about 0. They just
Correct.
increase. The x average is going to increase linearly, and x squared average is going to be a curve.
Okay, yeah, you're close. So you can see if this is asymmetric, that means you have a bias to go towards right, the average cannot be 0. Does this make sense? So what happens in this case, the average is non-zero, it's clear, and x squared average, previously you had, like for symmetric random walk, you had something proportional to t. You had this, correct? X squared average was increasing linearly time, but now you have a component where x squared average is going to increase linearly as t squared. So you have like sum of two terms. Square, one term proportional to time, the other term proportional to t squared. Okay. And let me change this to capital T, the interval for each random walk. Now what happens in the extreme case? So suppose you keep increasing this from 2/3 to 3/4 and then decrease this to 1/4. What happens to these two coefficients? Which one starts dominating? The t squared term, correct? So what is the extreme limit in this case for this random walk?
1 and 0.
1 and 0. So suppose you have probability 1 to go to right and probability 0 to go to left. Then what happens in x squared? Is you don't have this at all. You simply have x squared equals t squared. So if you consider a random walk with extreme limits, so p equals 1 to go to a right and q equals 0 to go to left, you are going to see x average is not 0, x average is increasing some constant times t, and x square average is going to be some constant time t square. Does this make sense to you? Yes? So now if the process is deterministic, can you describe this by a differential equation? So what's the simplest description of this process? So imagine you jump length L in a time interval t. So you can think a small change delta x divided by delta t equals L over t. Tell me if you don't understand this. This also kind of refreshes your memory on the concept of derivatives. Okay? So delta x is the small jump length, and delta t is the time. Okay? And right now I took the step to be L, and the time step size is capital T. So if I take the limit delta t tends to 0, and since L and capital T are constants, for example, let's take the ratio to be V, okay, which is a constant. Tell me if you don't follow this. Is okay? Are you with me? So this I can write for small time step size, dx dt equals V. And does this look familiar to you? Yes? What is this motion? This is motion with a constant velocity. So you roll a ball, not roll, but push a ball to move, like slide on the surface with constant velocity V. This is the equation that describes the motion, correct? And do you know the solution for this? What is xt? V times t. If you start from the origin at t equals 0, then xt equals vt. Correct? So it's a bit subtle that if you consider the random walk, until you hit the extreme limit, the process is still stochastic. Still, it's a random process. Okay? You cannot write a differential equation except the very extreme point. You need to do Monte Carlo simulation, and you don't have any equation for xt like this except for that extreme point. Does this make sense? But once you reach the extreme point, when you only go to the right, then you can write such a differential equation, and you have a nice solution xt equals vt. So this is probably the simplest possible differential equation you can write, like dx dt, the first derivative equals to a constant, and a simple integration gives you the solution. Okay? A little bit more complicated situation, you can envision even this problem. Suppose your jump length is not a constant. It depends on the position where you are at. Okay? So dx dt in this case, what is this? Suppose I tell you that the jump length is proportional, linearly proportional to the position itself, like the position where the particle is at. So what should I write here on the right-hand side? It's linearly proportional to position.
So constant times x.
Right. So it's kx. Okay. So this is slightly more complicated equation than what I have done here. But now this is already it's simple. It's has an analytical exact solution, but it can already describe a biological process. And can you think of a simple biological process which it can describe? Forget about position. Think of something else. Number of molecules, number of cells.
Cell growth.
Yes, that's right? So if you suppose you have n0 number of cells to start with, t equals 0, and then you want to write dn dt, where nt number of cells at time t. Okay? So dn dt, you write r growth times n, some constant, rg, or should I write as k? That's fine. So rg is a constant. So the number of cells you are growing in a system is proportional to the number of cells at that time. Okay? It's as simple as that. And if you look at the functional form, like the form of the equation, they are identical. dx dt equals kx, and dn dt equals rg times n. Now, you can also think that it might have a decay rate. So suppose some of the cells are dying, so you can add another constant, rd, and write this rg minus n minus rd n. Okay? And I can group them together to write rg minus rd n. And let's call this as a constant k, so it's k times n. So the equation now becomes dn dt equals k times n, where k is a constant, rg minus rd. So you started seeing already that how you can write very simple differential equations. It's not always simple. To describe more complicated or complex processes, you are going to encounter more complicated and difficult differential equations, and they might not even have such nice analytical solution as this equation has. And do you know how to solve this equation? I'm going to come back to that in a minute, but just to give you some motivation, you can simply change sides and write the solution nt equals. I'm going to come back to this solution one more time, so if you don't understand it now, it's okay. Don't worry too much. So I'm going to come back to this solution. So it has, depending on whether k is positive or negative, that means whether the growth term part is dominating or the death part is dominating, you have either exponential rise or exponential decay. There are two possible solutions, depending on whether rg is greater than rd. And if they're equal, then dn dt is 0, so there is no net change in the system. Now, typically the way like the modeling works, mathematical or computational modeling, that you first encounter a biological problem. So here the biological problem is, suppose in a beaker or in a culture you have some cells n0 at time 0, and you want to estimate how fast they are growing, okay? Or what's the nature of their growth. And you first make the simplest assumptions like this, that you assume dn dt is k times n, and you solve the equation, and then the next step will be